Okay, we're going to look at another probability problem. This one involving putting marbles in a hat, or marbles in a hat. So we're going to place 10 marbles in a hat, 4 red, 3 blue, 2 green, and 1 black. We can ask a bunch of questions about this. So one thing to keep in mind is, are we going to draw 1 marble, or are we going to draw multiple marbles? And if we're going to draw multiple marbles, are we doing it with replacement, meaning take a marble out and then put it back in, or are we going to do it without replacement, meaning take a marble out, leave it out, and then draw another one? So different types of problems for the same scenario. Drawing 1 marble out of a hat, usually most people are pretty quick on these. Draw 1 marble and find the following probabilities. So again, if you want to pause and write these down, or if you do, maybe give yourself 2 or 3 lines between each part. And the trick is, I not only want the answer, but I also want the notation. So first problem, find the probability that marble is blue. I can write probability that it's blue. Oops, I moved this down, so that's actually in the wrong place. That should be down there. Sorry. Come on. Find the probability that it is red or green, or the probability that it is not black. So I can put the bar over the black, not black. So the probability is blue. Well, there are 3 blue marbles out of 10. I can leave it as 3/10, or I can change it to a decimal, 0.03. Probability that it is green or red. I have 4 reds, and I have 2 greens. I can add that up, giving me 6 out of 10, or 0.6. And the probability is not black. 9 of the marbles are not black, so 9 out of 10. I could also think of not black as 1, the total probability, minus what if it was black, 1 out of 10. 1 minus 1/10, again, 9/10. Moving on to drawing 2 marbles. So first we're going to draw 2 marbles with replacement, and what that means is that the draws are independent of each other. Second draw does not depend on the first draw. So when we do with replacement, that means that they are independent. Okay, so the probability that both marbles are blue, again, the notation, probability of blue, blue. So the first one being blue has a probability of 3/10. And then I multiply those probabilities together. The probability the second one is blue is also going to be 3/10. And again, why are we multiplying them together? Because of the independence. If you have independent events, you can find the probability of 2 of them occurring using the idea that probability of A and B sorry. Okay, I'll take it out instead. Sorry about that. I wasn't going to write the formula down, but I think it might be useful here. Probability of A and B is just going to equal probability of A times probability of B, and that's because of the independence. Okay, so the probability both marbles are blue, 3/10 for the first one being blue, put that marble back, and it's 3/10 again for the second one being blue. Multiply those, you get 9/100, excuse me. The next part, sorry. So we're going to do this multiplication of the two probabilities for all of number 2 here, because all of number 2, when you put the marble back, has independence. The probability that neither marble is green. So that's the choices of not green for the first marble and then not green again for the second marble. The probability the first marble is not green, there are 2 green marbles, so the probability it's not green, 8 out of 10 for the first marble. And again, because I'm putting it back in, it's 8 out of 10 for the second marble. Multiplying those together because of the independence, get 64 out of 100, or 0.64. Next problem, the probability that the first is red and the second is green. So red, green. The probability that the first is red, let's see, we have 4 red marbles, so that's 4 out of 10. Put that red marble back in. I still have 10 marbles, 2 of which are green. So times 2 out of 10, that's 8 out of 100, 8 hundredths. The probability that the second is blue, given that the first is red. Well, let's see. So we're going to take some space here. I can set up my fraction bar. Pen is being very irritating. Set up my fraction bar here. Why is it doing this? Sorry. It's so good on the last video, but this one is just not working. Okay, so what's the probability that the first one is red? I'm going to put that in the bottom. There are 3 red. I'm going to lose the pen. Sorry, I'm going to do it without the pen. Delete. Pause the recording for a second. So I'm going to look at the formulas for this conditional probability over here. And if we recall, so here's where I think I do want to use the formula. If I recall, over here, the probability of B given A. Oh, why is it doing that? There we go. B given A. That is equal to the probability of the intersection A intersect B divided by the probability of A. So in this case, A is that the first one is red, and B is that the second one is blue. But because we're... Why? So the probability that the first one is red is 3/10. So I'm going to put that on the denominator here. I'm actually going to use the formula here because it'll help us with the next conditional probability when they're not independent. So in this case, because they're independent, the second one is not depending on what I drew in the first one. So when I draw the first marble and get a red, that has a probability of 3/10. I then put it back. The second one being blue is independent from that because I just put the red one back in. So that intersection, A intersect B, is just the probability of B. So in this case, because of the independence, this probability of A intersect B is equal to the probability of B times the probability of A. I'm so confused. I think I messed this up. I'm going to pause again. Sorry. Be right back. Okay, I'm back. Sorry about that. So because of the independence, the probability of A intersect B is going to equal the probability of A times the probability of B. And then we're going to be still dividing that by the probability of A. So you could think about this. These probabilities of A's are actually going to cancel out. So why is that happening? Well, because I'm putting the red ball back in, the probability the second one is blue does not affected by the fact that the first one was red. So if I wanted to use this whole fraction bar, again, I would have a 3/10 for the first one being red, and then times probability the second one is blue. There's 4 reds. So these numbers are wrong. I'm going to erase them. It should be 4/10, but I'm actually going to just erase this whole fraction here. Okay, because of the independence, this intersection's probability is probability of A times the probability of B. Probabilities of A cancel out, and then we're just left with the probability of B. And that's, remember, what it means when you have independence. Probability B given A has to equal the probability of B. So we're done over here. I made this harder than I needed to. It has to do with the second part where they're not independent, but in this case they are independent. The probability that the second one is blue is just 3 out of 10. Given that the first one is red, it's still just 3 out of 10. I'm going to pause the recording so I can work ahead and change that answer. I got it wrong initially. Okay, so the conditional probability the second one is blue, given that the first one is red, is just equal to the probability the second one is blue, which is 3 out of 10. And then again, that's because of the independence. The last one, the probability that both marbles are black. Again, we have only one black marble, but we take it out, then we put it back in. I get 1/10 times 1/10, which is equal to 0.01. Okay, so we're moving on to the third problem, where we're going to draw 2 marbles from the bag, this time without replacement. So as you take a marble out, it changes potentially the total number of marbles in the bag. So, I mean, actually it changes, we go from 10 down to 9, but it also can change the color of what's left. So let's see how this works. Again, we're going to multiply probabilities, but we need to do it in a way that takes into account that something has been taken out. So I just re-put what we have in the bag here so I can see it. 10 marbles in the hat, 4 red, 3 blue, 2 green, and 1 black. Find the probability that both are green. So the probability that the first one is green still is 2 out of 10. But now we've taken that one out. So we're going to multiply by the probability of the second one being green, and there's only 1 green left because the first one is taken out, and then we only have 9 total marbles left. So it's 2/10 times 1/9 and decimal 0.02222 repeating. So the probability that the first one is red and the second one is blue, so I write the notation probability of red, comma blue. You know, you'll notice all the problems involving blue or black, I'm actually writing the color out. That's because both blue and black start with B. I should have used a different color so that I could just use the letter itself, but it's never a problem to write more inside the probability notation. It just makes it more clear. So probability the first one is red. Again, we have 4 reds, so that's 4 out of 10 times, now we've taken 1 marble out, there are 9 left, and of those 9, 3 of them are blue, so 3 out of 9. So in the previous problem, we had 2 greens, 1 of them came out, so that only left 1 left. In this problem, because I'm taking the red out first, we still have 3 blues left. And I could write that as, 12 over 90 and then reduce it, or 0.133333. Let me just write that down. 12 out of 90. Divide them both by 2. That'd be 6 out of 45. I wanted to keep reducing that. 3 goes into both of those. 3 goes into 6 twice. 3 goes into 45 15 times as a reduced fraction, 2/15, and again, 0.133333. 3 more. The probability that neither marble is blue. So that's not blue followed by not blue. So again, when we do a complement or the not of something, I can write the word not in front, or I can put the bar over the top, like up here I did not green and not green. Here I wrote not blue and not blue. The probability the first one is not blue. There are 7 that are not blue out of 10. And we multiply that by the probability the second one is not blue. So I took one of the ones that was not blue out, so there are only 6 that are not blue left, and there are only 9 total marbles left. And reduce that down. 0.4666 repeating, or rounded 0.4667. The probability the second one is blue, given that the first one is blue. So this is a conditional probability, and again, this time they're not independent events. So if the first one is blue, we take that marble out. What's the probability that the second one is blue? Well, it could work similarly as the last problem. So I just come over here for a second. Move the pad instead of moving my pencil. Sorry. So I might have to pause again because I'm having issues with the pencil. There we go. The probability of, in general, B given A is the probability of the intersection divided by the probability of A but what's the probability that you got 2 blue? So the intersection is that the first and the second one were blue. So that would be the first one being blue is 3 out of 10. And then we would multiply by the probability the second one is blue, and that's 2 out of 9 because they're not independent. And then we would be dividing by the probability that the first one is blue, which would be 3 out of 10 again. You can see, similar to the last problem, this probability that the first one is blue is canceling out, and we're left with, well, in this case, it depends on the fact that we took a blue one out already, but the probability is the same, 2 out of 9, because those 3 out of 10s cancel out. So not the same. In the first one, it was still 3 out of 10 because we put the red one back in. In this one, we take a blue one out. There's only 2 blue left, 9 out of the 9. Hopefully that makes sense. And it's a little bit of a tricky problem to do these conditional probabilities with the drawing of the hat. But it has to do with the fact that it's happening in order. So one's happening first, then the second one is happening. So if we know the first ball is gone and it's blue, there's 9 marbles left, 2 of them are blue. So that probability that the second one is blue, given the first one is blue, just 2 out of 9. Okay, the last problem, probability that both are black. Well, there's only one black marble, so probably the first one is black is 1 out of 10, but then there are no more black marbles left. So that would be 0 out of 9. So that probability is 0. And that's the whole problem. I would reiterate sort of the 3 different parts of this problem. One, when you're just drawing one marble, usually pretty straightforward. The next part, where you're drawing 2 marbles with replacement, and that part has to do with independence. And then the last part, you're drawing 2 marbles without replacement, which can change both the numerator and the denominator depending on what happens within the draw.